All right, over the next couple of lessons, we are going to be looking at systems of equations. We're going to start by looking at systems of linear equations. And this first video is going to be a quick review of what you learned in Algebra 1 and Algebra 2 about solving systems of equations. So first, remember that what we're really looking for here is we're trying to find an ordered pair that these two lines have in common. Graphically, that would mean where the two graphs intersect. But graphing the lines, unless you have the aid of technology, is very inaccurate. And so that's why we have an algebraic way of doing this. So the first is, how do we know if an ordered pair is a solution to this system or not? And so as with anything, we can test these by plugging in these values here. So if we have the ordered pair 1, 2, that means that x is 1 and y is 2. So we're going to go ahead and plug that in. So I'll start with the top equation. So I have 2 times 1 minus 3 times 2. And the question is, does that equal -4? Well, that's 2 minus 6, which will give me -4. So that is a true statement. That does not, however, mean that this is a solution to the system, because so far I've only shown that it's a solution to the first equation. I also need to check in the bottom equation. So 2 times 1 plus 2, which is the y value, we want to know, does that equal 4? So that's going to be 2 plus 2, which does equal 4. So we got two trues. So the answer is yes, that ordered pair is a solution to this system of equations. It must be true in both to be a solution. So we can go ahead then and try the same thing on the next example using 7 as our x and 6 as our y. And here's what happens when we plug that into the first equation. We end up with 14 minus 18, which does in fact equal -4. So that's good. So now we move on and we check it in our second equation. So this is what we get when we plug in, and you can see pretty quickly here that when we work this out, this is not going to be true. You're going to get 20 equals 4. So this is a false statement. Since I did not get true for both, the answer here would be no, okay? You got to get two trues for the answer to be yes. A single no means that it is not a solution to the system. It's a solution to the top equation, not the bottom equation, which means it's not a solution to the system. Okay, the next thing that I want to refresh your memories on is the substitution method for solving a system of equations. So the substitution method is useful when we are able to quickly solve one of our two equations for one of the variables. And you can see here, this bottom equation already has just a 1y. Sorry. So we can very quickly subtract 2x from both sides, and that gives us y equals 1 minus 2x. Now, what this means is that no matter what y is, it is always going to be equal to 1 minus 2 times whatever x is. That's always going to be the relationship between x and y. So since we then know that that is always true, that means that I could take out the y from this first equation and replace it with what I know that y is equal to, which is 1 minus 2x. And so that's what we will do. I'm going to take this top equation, and 3x is going to stay the same, plus 2 times. Instead of y, I'm going to make the substitution of 1 minus 2x. And that still is equal to 4. Now you can see that I have an equation that only has x's in it, which means that we can go ahead and solve. So we're going to do a little bit of distributing. We're going to combine our like terms. So we get -x plus 2 equals 4. Subtract 2. And then divide by -1. So we get that x is equal to -2. But we are not done, because remember that we're trying to solve for two variables. Now that I know what x is, I can come back over here to what I know that y was, and I can plug in. I know now that y is going to be equal to 1 minus 2 times whatever x is, and we know now that x has to be -2. So we get 1 plus 4, so y is equal to 5. Now again, what we just found is if we were to graph those two lines, the single point where these two lines would intersect would be the ordered pair -2, 5. And so we always write our answer as an ordered pair. So that's how we can use the substitution method. Another method that you learned for solving systems of equations is the addition method, which you may have heard called the elimination method. Our goal is to multiply one or both of the equations to build opposites. Opposite in math, remember, only means positive versus negative. That's the only thing that opposite ever means. So 2x and -2x are opposites. 4y and -4y are opposites. So that is what we are trying to make happen. So if I look at this first example here and these two equations, I see that 9 is a multiple of 3. So I could eliminate the x's pretty easily. We could do the same with the y's. 8 is a multiple of 2. So it looks like I'm only going to have to multiply one of these equations. I'm going to choose to multiply the top. So I'm going to multiply this top equation. I'm going to start by thinking about multiplying by 3. That's going to get them both to be 9x. But again, remember, we want opposites. 9x and 9x are not opposites. They're exactly the same. So I need to multiply by a negative so that I can switch all of those signs. Now, here's what our system becomes when I multiply. The top equation becomes -9x minus 6y equals -144. And then we haven't done anything to the bottom equation because for this one we don't need to. So we're just going to recopy it. And that's -24. Okay, so we haven't changed it. This is still the same system. We've just multiplied by a factor of -3 in the top. This is called the addition method because now we're going to add these two equations straight down. If we've done our math correctly, one of the variables should zero out, and the x's do. When I add, I get 0x. That's why we want opposites, and that equals -14y equal to -168. Now we have an equation that just has a y. We can divide by -14, and really quickly we get that y is equal to 12. So again, that's half of an ordered pair. Now we need to figure out the x. Now you can plug it into any of the equations you want, one of the originals or one of the ones that we multiplied. I'm going to go with the very first one from the original problem because it has the smallest coefficients for x and y. So I know that 3x plus 2 times y, but now I know that y is 12, is equal to 48. So we solve that. We get 3x plus 24 equals 48. Subtract your 24, and then divide by 3, and we find that x is equal to 8. So again, those two parts help us determine that the ordered pair, that is the solution, is the ordered pair 8, 12. Remember that an ordered pair has to go in x, y order. So we found y first, but it has to be the second half of the ordered pair because of the order that they're supposed to go in. Okay, that one was really nice because everything was already lined up in columns for us. For B, we're going to go ahead and use the addition method as well, but right now they're not lined up in a way where we can add straight down. So our first step needs to be to rewrite these equations. Let's get ax plus by equals c form for both of these equations. So here's what we get when we do that. Now, on the previous problem, we only needed to multiply one of the two equations. Hopefully you can see that in this example, that's not going to be the case. We're going to need to multiply both. Now, it doesn't matter which one you do. You have to make sure that you get them to have the same coefficient and that one of them is positive and one of them is negative. So I'm going to choose the y variable as my target because I already have terms that have opposite signs. If you wanted to eliminate x, you certainly can, but you would have to multiply one of them by a negative to get one of the signs to switch. But because these already have opposite signs, I don't need to multiply by any negatives. So what I'm going to do is I'm going to multiply these both to make 12. So I'm going to multiply the top one by 4, and I'm going to multiply the bottom one by 3. Essentially, I just traded the coefficients. So if I was going to do x, I'd multiply the top by 3 and the bottom by 2, and one of them would have to be negative. Again, it doesn't matter which one. So here's what we get now. 8x minus 12y equals 36. Whoops, 36. And then we get 9x plus 12y equals 24. And we can see that we've done a great job because when we go to add these two together, the y's are opposites and they will zero out. So we get 17x equals 60. And when we divide, unfortunately, 17 does not go into 60, so we get 60 over 17. Not a super friendly number, but we can work with fractions. Okay, just because you get a fraction does not mean that you are wrong. I just want to make that really clear because fractions, it's very rare that two lines are going to cross exactly on like a perfect ordered pair. The other thing, remember, is that we always want to work in exact values whenever possible. So I'm not going to change this to a decimal because it certainly will be something that I have to round, and I'm going to avoid that if I can. Now, when we go to plug this back in, we're going to have to do a little bit of work with common denominators and stuff, but here is what we end up with. So I converted everything to 17ths so that I could work with my common denominator. And so this ends up giving us negative 11 17ths for y. So our ordered pair is going to be 60 17ths, negative 11 17ths. Not the most friendly numbers, but they will work just fine. The last thing that I want to look at is the three types of solutions that you can get, okay? So all the ones that we have seen so far follow this first scenario of exactly one solution. The two lines intersect, and what we are finding is this ordered pair right here where the two lines intersect. But there are two sort of odd cases that can also happen. It might be possible that our two lines run parallel to each other. And what we know about parallel lines is that they're never going to intersect. So that would mean that there is no solution. The solution set would be the empty set, the null set, because there are no solutions there. Now, the other option is that the two lines end up completely overlapping on top of each other. And if that's the case, then there are infinitely many solutions. Those two lines coincide at every single ordered pair. Okay, so here's what that will look like algebraically when you go to solve those systems, if that is what you're going to get. So I look at example A, and we need to decide, do I want to use substitution or do I want to use elimination? I don't see a variable that I could quickly get by itself, so I am going to use elimination, the addition method. And so I'm going to multiply the top equation by positive 2, and that should get my x's to zero out. So you can see after you multiply that something even stranger is happening here. Not only do my x's zero out, but my y's do as well. So that means that on the left side of my equal sign, I have nothing left, which means I have 0. On the right side, when we add, we get 15. So the question is, when does 0 equal 15? And that would be never. This is always going to be a false statement. It is not possible for 0 to equal 15, which means that this system has no solution. They are going to be running parallel to each other, and they're never going to intersect. So that's what that's going to look like algebraically. You're going to get an equality statement that is impossible to be true. Okay, now looking at B, I see that this one already has my equation solved for y. So that's my clue that I'm going to use the substitution method. I'm going to remove the y from the second equation and use the substitution that y is equal to 3x minus 2. When we work all of that down, we end up losing our variables again. But this time we're left with the statement that 10 is equal to 10. Now maybe you subtract 10 from both sides, that's fine. You get 0 is equal to 0. Either way, this statement is true. And when is it true? It is always true, no matter what. So what this means is that there are going to be infinite solutions to this system of equation. And so if there's infinite solutions, that means we have to describe what they look like. There's infinite solutions, but it does not mean all real numbers. Okay, that's really important. Because the only places where this is going to be true, again, what is happening here is that I have one line going in one spot, and then I have another line that is tracing the exact same path. None of the values out here would make either of those true because they're not on the line. So we have to describe the types of equations. And anytime we need to describe a set of numbers, we want to use set builder notation. And so here's how we would write this. And you can write it one of two ways because there's two different equations. We're going to say the set of all ordered pairs x, y such that y is equal to 3x minus 2. That's one rule that we could use. So for example, if I picked 7 for x, that would mean 21 minus 2. So that would be 19 for y. So that would fall in that set. Any ordered pair that follows the rule y equals 3x minus 2, aka is on that line, would be fine. The other option would be to use the other equation, the set of all ordered pairs x, y such that 15x minus 5y equals 10. So again, as long as your x and y follow that rule, giving you a sum of 10, then it's going to be true. So that's how we would write our answers if there are infinite solutions. Either one of those orange statements in set builder notation would be just fine. So that's just kind of a rundown of systems of linear equations and the algebra that you need to know for the rest of this week and all of next week. We are going to then focus on some of the applications of systems of equations, like how might this apply to your future career or future majors or things like that. So I will see you guys soon.